Right now, as you're watching this, quantum tunneling is happening in the enzymes in your body, helping speeding up chemical reactions billions of times faster. Birds flying overhead are literally seeing Earth's magnetic field thanks to quantum entanglement in their eyes. And according to some scientists, every decision you make might split the universe into multiple realities. Sounds like sci fi. That's just Tuesday in the quantum world. But here's the crazy part, people are claiming quantum mechanics proves we are hologram, that we can become immortal, or that we are living in a simulation. Some even think we can time travel or levitate using quantum effects. So, what's real quantum science and what's quantum nonsense? Let's find out. But first, what is quantum mechanics? Quantum mechanics is the study of matter and energy at the smallest scale, typically atom and subatomic particles. But to understand why it's so revolutionary, we need to look at how it developed. Top 7 turning points in quantum mechanics history. In 1900s, Max Planck solved the blackbody radiation problem by proposing that energy comes in a discrete packets called quanta, but he thought his own idea was ridiculous and saw it as just a mathematical trick. Einstein came along and said, actually, Planck, your crazy idea is right, extending quanta to light particles, photons, and winning the Nobel Prize for explaining the photoelectric effect, not relativity. But the plot twist was, even Planck found Einstein's extension of his own idea ridiculous. Meanwhile, Louis de Broglie suggested that particles like electrons also behave as waves. Squander just developed wave equation to describe this, but hated the idea of superposition so much he created his famous cat paradox to mock it. Heisenberg created an entirely different mathematical approach, metrics mechanics, that even Scottists couldn't understand at first. 5 quantum concepts and what they don't mean. First, wave-particle duality. At the quantum scale, matter and energy exhibit both wave-like and particle-like properties, but never both simultaneously. Which behavior we observe depends on how we measure them and their environment. But does this make us hologram? The holographic principle in physics suggests that all information in 3D volume can be encoded on its 2D surface, like how hologram works. But this does not mean we are fake. It's a deep mathematical relationship between quantum mechanics and gravity that might help us understand black holes and the structure of space-time itself. Second, uncertainty principle. At quantum scale, there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. The more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. This isn't due to measurement limitation, it's built into the fabric of reality. Fun fact, Heisenberg discovered this principle while recovering from hay fever on the German island of Heligoland, working without any physics books. Third, superposition. Before measurement, quantum particles can exist in a multiple states simultaneously. It's like a coin that's spinning in the air. It's neither head nor tail until it lands. The key difference at quantum scales, the spinning state is real and can have measurable effects. Why doesn't this work for big things? Larger objects interact with countless particles in their environment, causing rapid quote-unquote decoherence. The superposition collapses almost instantly. That's why you cannot be sitting and sleeping simultaneously. Or can you? Even though your atom technically could be in superposition for incredibly brief moment. Quantum consciousness myth. Can humans create reality with their thoughts because of superposition? No. While consciousness might play a role in a certain interpretation of quantum mechanics, there is no evidence that human thoughts can influence quantum system any more than a simple measurement device can. Simulation hypothesis. Some believe quantum weirdness like superposition prove we are in a matrix-like simulation. While this is taken seriously by some physicists as philosophical speculation, it remains unprovable and unfeasible, not really science. Quantum immortality. Based on the many world interpretations, some think consciousness jumps between universes when we die. While many worlds is a legitimate scientific interpretation, consciousness jumping between realities has no experimental evidence. Fourth, quantum entanglement. When two particles become entangled, measuring one instantly determines the state of the other, regardless of distance. If electron A has upspin and electron B will have downspin, even if B on Mars and A is on Earth. Einstein called this spooky action at a distance because he thought it violated relativity. Key point to be noted, no information actually travels between the particles. The correlation was established when they first interacted. It's like having two coins that are guaranteed to land on opposite sides, no matter when or where you flip them. Fifth, quantum tunneling. Particles can sometimes pass through energy barriers that should be impossible to cross classically. It's not teleportation, it's more like the particles borrows energy briefly to get through, then pays it back on the other side. But can we time travel? No, quantum tunneling involves particles moving through space barriers, not time barriers. While some theoretical physics explore connection between quantum mechanics and time, particle time travel remains science fiction. Sadly. Quantum levitation. Superconductors can float above magnet due to Meissner effect. This is real quantum physics in action. However, it's not anti-gravity that could lift spaceships. It only works with specific materials at extremely cold temperature, often requiring liquid nitrogen or helium, and only repel magnetic fields, not gravity itself. Now moving on to next part. Top 4 real quantum application. Quantum computing. Quantum computing uses quantum bits, qubits that can exist in superposition of 0 and 1 simultaneously. Google's Sycamore quantum computer performed a specific calculation in 200 seconds that would take the world's most powerful classical computer 10,000 years. However, this was for one very specific problem. Quantum computers won't replacing your regular computer for most tasks. Quantum biology. Plants use quantum coherence in photosynthesis to test multiple energy pathways simultaneously, choosing the most efficient one. Enzymes in your body right now are using quantum tunneling to speed up chemical reactions that would otherwise to be too slow for life. Migratory birds navigate using quantum entangled electron and cryptochrome proteins in their eyes. When light hits this protein, Earth's magnetic fields affect the quantum state, essentially letting them quote-unquote see magnetic field lines. Quantum cryptography. China's Messier satellite enabled quantum key distribution for ultra-secure communication. The security comes from quantum mechanics itself. Any attempt to intercept the quantum keys automatically disturbs them, alerting both parties to the breach. Quantum sensing. Atomic clocks use a quantum transition to measure time and with incredible precision. They are accurate to within 1 second over 15 billion years. The precision is essentially for GPS satellites, which accounts for relativistic time differences to maintain accuracy. Moving on to the last part, and very important question. Why quantum effects usually stay small? Here's the crucial point often missing from pop science. Quantum effects typically only appear at incredible small scale. Extremely cold temperature or very short time periods. The larger and warmer something gets, the faster its quantum property gets. Quote unquote washed out by interaction with the environment, a process called decoherence. A typical bacterium experiences decoherence in about 10 to the power minus 13 seconds. A human, even faster. That's why we don't walk through walls or exist in multiple places simultaneously. Too bad. From quantum thermodynamics to quantum gravity, trying to unify Einstein relativity with quantum mechanics, we are still uncovering fundamental truths about the reality. Current research into black hole information paradoxes, the quantum origins of the universe. Closing statement. Quantum mechanics reveals that reality is far stranger than our everyday experiences suggest, but it's also more constrained than popular myths claim. While we can't time travel, levitate, or create reality with our thoughts, the actual quantum world, with its genuine application in computing, biology, and cryptography, is far more incredible than any science fiction. Tell me what you think about this video, share your thoughts in the comments, subscribe for more videos such like this, and like. Make sure to like, please.